good afternoon, everyone, and welcome to today's session. Thank you for joining us today for this exciting and informative session on graph neural networks. My name is Rahil Siddiqui from Pharmedic, and I'll be the moderator for today, guiding us through the session. I'm joined by my wonderful team at Pharmedic, and my team will be happy to provide assistance or technical support anytime during today's session. So before we dive deeper, uh, at Pharmedic, we develop digital health systems focused on medication safety, combining clinical workflows with evidence-driven decision systems. Our aim is to reduce adverse drug reactions and improve treatment outcomes at scale while advancing a shift towards preventative, personalized care aligned with the UAE's long-term healthcare innovation agenda. Before we dive in, I'd like to cover a few notes. This webinar will run for approximately 1.5 to 2 hours with a Q&A session during the last few minutes. Feel free to send your questions at any time using the chat feature. We will address them during the Q&A session. We will have a feedback form at the end of today's session, which is needed to confirm attendance and share certificates. We will be recording this session and may share the recording link with the registered attendees. Now, join me to introduce and welcome our distinguished speaker who will be leading today's session. So Dr. Mostafa, he has received his PhD in medical image analysis from the University of Girona, Spain. He is currently working as a postdoctoral research associate at Mohammed bin Zayed University of Artificial Intelligence in Abu Dhabi. Dr. Salem's work sits at the precise intersection we are exploring today, cutting-edge AI methodologies applied to real-world healthcare challenges. His research has led to multiple high-impact publications in artificial intelligence for healthcare, contributing to our understanding of how advanced machine learning techniques can improve patient outcomes and transform medical diagnostics. Dr. Salem, thank you so much for joining us today and sharing your expertise with the community. Over to you, Dr. Salem.
Thank you, Rahil. Thank you for your introduction. Can we start now?
Yes.
Okay, I will share my screen. Okay, let's start. Good afternoon, everyone, and welcome to this tutorial on graph neural networks, foundation and medical application. My name is Mostafa Salem. I'm a postdoc research associate at Mohammed bin Zayed University of Artificial Intelligence in UAE, Abu Dhabi. Over the next 90 minutes, we will take a journey from the fundamental of graph neural networks, how they work, how they are powerful, and how they differ from traditional deep learning architecture. And then we will move toward learning their application in the medical domain, including how they can model biological structures, medical images, etc. Please feel free to note down your question. We will leave time at the end for discussion. So let's start with the agenda. Here is an overview of what we will cover today. We'll start with graph fundamentals, where I will introduce what is a graph, the key concept like nodes, edges, and adjacency matrices, and how graphs are such a powerful way to represent relationships in data. Next, we will move into graph neural networks, where we will see how deep learning can operate directly on graphs. We will look at the architecture, message passing, and how GNNs generalize convolution to a regular domain. Then we will get hands-on with PyTorch Geometric, which one is the most powerful framework to building graph neural networks. I will take you through code examples so you can see how graph data is represented, how layers are defined, and how to train simple GNNs. Finally, we will explore vision in graph, which I will discuss how GNNs are being used in computer vision, how to deal with images using graph. And by the end, you should have both a conceptual understanding and a practical sense of how to apply GNN in your research domain. So let's start with graph fundamentals. So what is a graph? Before we dive into the technical side, let's first build some intuition. So what's a graph? A graph is just a way to represent objects. Graphs are all around us. So graph is just a way to represent objects and the relationship between them. Think about how many things in real world are defined by connections, like friends are connected in social media, molecules made up of atoms connected by chemical bonds, or even diseases connected through shared genetic or clinical features, and a lot of examples that can be represented as objects and relationships between these objects. So a graph consists of two main parts. First is the nodes, as you can see in the figure. So nodes are the objects or the entities like people, proteins, pixel, etc. Then the edges which are the connection or the relationships between them. And then both nodes and edges can represent the whole graph. So graph is basically mathematical structure that tell us who is connected to whom and what interact with what. So let's see some graph data examples. So social networks graph, this is one of the most intuitive examples to show graph and the relationships. These are widely used in natural images. So each node could represent a person, and the edges show friendship or interactions. Knowledge graph, these are, as I mentioned, they are widely used in natural language processing and recommendation systems. As you can see, relationships between concepts. So each node represent a concept, and the edges represent relationships between these concepts. And finally, the molecular graph. As you can see, nodes are atoms in this example, and edges are the chemical bonds, and this is very commonly used in drug discovery and bioinformatics. So these are just three simple intuitive examples of graphs, and just to let you know that anything in your domain you can think of as a graph if you could represent nodes and edges, with nodes represent entities, objects, whatever you can see in your domain, and the edges are the interaction between these nodes related to your domain. So anytime we care about relationship structures or interactions, graph give us a natural way to represent and analyze that information. This is very message I want to let you know when to use graph in your research. If you have data, if you could represent these data as nodes, if you have structures, if you have relationship, if you have connection between these data, between these objects. So graph is the best and machine learning architecture you can use to learn and to get to learn a good representation from your data. So, and I think you are coming from different fields. So, can you think of a case in your field where data could be modeled as a graph rather than a grid or a sequences? One answer. Okay, we can leave this to the end of the lecture, so you can like think of an example of your domain that you can use the graph, and the graph data in your domain. So graph representation. Now let's move to the graph representation. As I mentioned before, node, edges, and the graph level feature. So when we talk about the graph in machine learning, we don't just mean the structure, but we care about the feature or the attributes attached to different parts of the graph. As you can see in the figure here, each node, an edge, or even the entire graph, we can store information in this structure. So For nodes, we will have something called node feature. For edges also, we can have something called edge feature. And also for the whole graph, we can have a feature represent the whole graph. So now we will deal with what's called node embedding, or what's called edge embedding, or what's called graph, or the whole entire graph embedding. Let's see this example. This is a molecule for ethanol. Uh, if I have this structure, I want to represent it as a graph. So nodes will represent atoms. So what about the feature of this atom? Each atom will have embedding. This embedding will have the letter of the atom, the atomic number, the variance, the charge, etc. And the edges, which is the chemical bonds between atoms. So I can also add for each edge some embedding or some knowledge, some features, like bond type, single or not single, bond length, and any other information related to this field I can add to this edge embedding. So for the whole graph, for the whole structure, I can also add an embedding that represents the whole entire graph, like molecule name, formula for this molecule, molecule weight, etc. So when I'm talking about graph, I mean the structure, this number one, and also the features. I have three kind of features: node features, edge features, and the entire graph feature. So what are types of graph? For sure, we have different type of graphs. Let's see what are these types. We can divide the graph according to directed or undirected. So we have directed graphs and undirected graphs. In directed graphs, the edges has a specific direction from node A to node B. But for indirected graph, edges are bidirectional, means it's if A and B are connected, so it's connected bidirectionally. A connected to B and B is connected to A at the same time. Example of undirected graph is the social networks. If I'm friend to Rahil, for example, he also will be friend of mine. So this is undirected or bidirectional relationship between the entities or the nodes of the graph. The second category is weighted or unweighted graph. So weighted means I have a weight, a specific weight for each edge. So if I have an edge, I can add a weight to this edge, and we call this graph weighted graph. If the edges don't have any weights, we call this unweighted graph. So we have examples that we need to add, like the chemical bond, or the if I'm like if I want to present the traffic lights in Dubai, for example. So each traffic light will be a node, and the distance or the connection between two traffic lights will be the edge. I can add the distance between these two nodes as edge weight. In this case, I will call it weighted graph. So weighted graph, I can add distance, I can add similarity score, I can add correlation between the entities, or whatever information I need to connect these two nodes with each other. The third category, the third division is heterogeneous graph or homogeneous graph. So I have homogeneous graph, which all the nodes and edges are from the same type, and this is a very simple one. And I have also a heterogeneous graph, which I may have different kind of nodes and different kind of edges. So if I want to represent like professors, employee, students as a nodes, so I will have three different kind of nodes. And for sure, the relationship between students is a kind of edge relationship. There is a relationship between professor and students is another edge relationship. So I will have different kind of nodes and different kind of edge types. And in this case, the graph is called heterogeneous graph. Okay. The third division is dynamic and static graph. So static graph means the structure is the same. I have a predefined number of nodes and number of edges. And the other one is the dynamic graph, which edges and the features are changed dynamically. So maybe I can have now 30 edges. Maybe after some time, the edges number changes, the connection changes. So the structure is not fixed in this case, like dynamic graph. For sure, this is I will choose one of these kind of graphs according to my research and my problem itself that I want to solve. So maybe if I'm working on traffic light prediction, and so I will have to use dynamic graph or dynamic weighted graph or dynamic weighted heterogeneous graph. So the graph could be dynamic, could be at the same time heterogeneous, could be at the same time weighted, and could be directed. So these kind of graph are not exclusive. You can have different category at the same time. So after this distinction between the different kind of graph, I want to know how to use this graph, how to write code for this graph. So I will move to what's called GNN. GNN is graph neural networks, and these are the deep learning architecture I will use to represent graph and to try to learn embedding and representation for each kind of for each entity in the graph. Okay. So the next question is how we can represent a graph in a computer. So we know what is a graph, what is the different category of the graph, and then we want to represent the graph in our computer. So let's talk about graph representation. For graph, I need to store what's called feature matrices. And these feature matrices are the feature for each node or the feature for each edge in the graph. So these matrices are what GNN will use as input to learn from this graph. So after having the graph, after having the structure of the graph, each node in the graph will have its own feature, its own data, and also each edge connected to nodes will have its own feature of its own data. So I will combine the feature for nodes in this matrix X, and also I will combine all the representation of edges in this matrix E. So X and E are the node and the edge feature respectively. Okay. This about the data, the representation. I want also to encode and to represent and to store the connection between nodes. How to store the connection? So I will use what's called adjacency matrix. So adjacency matrix is a 2D matrix that will tell you which node is connected to whom. So if you have like 4 nodes, so the matrix will be 4 by 4, and now each connection between 0 and 0, this is 0 means the node 0 is not connected to node 0, and this one means node 0 is connected to node 1, and 1 is not connected to 0, not connected to 1, but connected to 2, and etc. So the adjacency matrix is a 2D matrix, and each row, the rows and columns represent nodes, and the values will be zeros and ones. 0 means these 2 nodes are not connected, but 1 means these 2 nodes are connected. So by these 3 matrices, I have a graph. So the graph data will be represented in X and E, which are the features of the nodes and edges, and the adjacency matrix, which encode the connection, the structure between the nodes. Can you imagine this matrix? If I have graph with 100 nodes, this matrix will be 100 by 100. But what about if the graph nodes is 1000? So I will have this adjacency matrix 1000 by 1000. What about if a graph nodes is 1 million? So adjacency matrix as a 2D matrix is not a good option to use if your graph nodes are very high. So what the other option to represent the structure? I can use what's called edge list. So it is the same, more or less the same. It encodes the same information, but it will use less memory. That's why we say edge list is memory efficient. So if I want to use edge list, I will just store which node is connected to 1. So 1 is connected to 2, 1 connected to 3, node 2 connected to 3, node 3 is connected to 4. That's it. But if I want to use adjacency matrix, I have to use a n square entity. So it will use like order of n cubic memory. That's why it is not efficient as a memory for large graphs. The third kind of way to represent the structure of the graph is what's called adjacency list. In this case, for each node in the graph, I will just mention which node this node is connected to. So it's more or less like the edge list, but it is efficient for sparse graph. What I mean by efficient, if you ask me which node are connected to node 3, it's just order of 1, I will tell you 1, 2, and 4. If you ask me which nodes are connected to node number 2, it will be 1 and 3. So it's efficient to know what are the neighbors for each node. So to conclude this slide, this is a very important slide I will use in my code later on. I have to store the information of the graph. I have to store the structure of the graph. For the information, I just need to store the embedding for each node, which is matrix X, the embedding of each edge with the matrix E, and also I can store an embedding for the entire graph. And then I want to store and encode the structure of the graph. So I have 3 ways to store the structure of the graph: adjacency matrix, edge list, and adjacency list. For adjacency matrix, it is like it takes a lot of memory. It needs order of n square memory, so it is not efficient for large graphs. The second option is edge list. As you can see, it is very, very memory efficient. And the third one is the adjacency list, which is efficient for sparse graph and easy neighbors iteration. So now we know how to present a graph. Next question is, how can we use graph for learning? How to learn information from our data represented as a graph. So if you have a graph, we can do what's called node level prediction. So I have a graph. The graph is consisted of nodes. The nodes are connected by edges. So I have information related to each node, information related to each edge, and information related to the entire graph, the whole graph. So I can do what's called node level prediction, which I will predict a label or a property of individual nodes in the graph. For example, in brain connectivity network, I have each node will represent a part of or a region in the brain. So I will classify each region. In social networks, I can predict a user interest or a group membership. So this is, I will predict something for each node in my graph. The second one is link level prediction. So I will predict missing or future connection between nodes. So if I'm working in the social networks, I have 2 nodes. These are two persons. I want to predict in the future, are these 2 persons should be connected? And this is what Facebook is doing to suggest friends to you. So if you visit a place, if you open your GPS and the Facebook could detect your location, he will start to suggest you more persons that enable their GPS in more or less the same location. So they will predict if you should be connected to this one. So this is kind of what's called link level prediction. The third type of learning in graph is the graph level prediction. So I will predict a label for the entire graph, not for each node. So I can predict something related to nodes. I can predict something related to lengths or edges. I can also predict something related to the entire graph that I have. Like in chemistry, we can classify a whole molecule as a toxic or non-toxic molecule. So in node level prediction, I have a specific node. I want to ask a question about this node. Does this, if each node represents a person, so my question will be, does this person have a disease? I have to say yes or no. So this is a binary classification. In edge-level prediction, I have two nodes, and I want to ask, should this person buy this product? If you are in Amazon, and Amazon try to suggest products to you. So in this case, Amazon have a graph. You are representing a node in this graph. The other products are representing nodes in the same graph. And what is Amazon is doing is trying to predict if this product should be suggested to this person. And if the answer is yes, you will find this product as a suggestion by Amazon to you. So this is called edge level prediction. And the graph level prediction, I have the graph, I have all the nodes, I have all the edges, and I want to ask a question related to the entire graph. So is this molecule is a suitable drug, yes or no? So you have to answer according to the information related to the entire graph. So how we can learn these embeddings for node, edge, or graph level prediction? GNN is our way to learn the node embeddings, the edge embeddings, and the graph embeddings, so we can use these embeddings to do classification or regression. Let's start the second part, which is graph neural networks. I think I can take some question about the first part. If anyone like have any question about the first part, so when to move to next the second part, you will like have your question answered.
We have a question in the chat actually. So it's by Mahra. In your field of work, can you share a concrete example where a graph or machine learning model is used to identify patterns, support decision making, or predict outcomes? And how does this approach add value compared to traditional methods?
I think I have to show the second part to answer this question because like it's not related exactly to the first part.
Mhm.
No,
I
is
had
there any question about nodes, edges, how to present graphs, different kind of graphs, and only this part?
Currently we don't have any questions, so
Okay,
I believe we can
I will continue. Okay, it's okay.
proceed.
So now let's start with what's graph neural networks. So graph neural networks is just like the other traditional machine learning architecture, like MLB or CNNs. I'm not sure if most of you are familiar with what is MLB, multi-layer perceptron, or CNN, convolution neural networks. But these are kind of machine learning or deep learning architecture that can deal with image data. So with image data, like the image you can see now in the slide, it's a fixed grid structure. And also tabular data, which are the like for each row, I have a specific the same number of features. These two kind of data can be used and can be used to as input for MLB or CNNs. But for the graph data, I cannot use MLB or CNN with graph data. Why? Because I cannot apply. Why I cannot apply GNN and MLB directly on graph data? Because graph are non-Euclidean. There is no grid. Like if you see in the image, you have the width and height, you have a fixed pixel, number of pixels for each image. And also for the tabular data, you have, for each row, you have a specific fixed number of features. But for the graph, I don't have fixed number of nodes. I don't have fixed number of edges. So I cannot apply directly MLB or CNN to the graph data. If you try to flatten the graph into vectors, we will lose the connectivity. So like if I have a graph of 5 nodes, I can, okay, take these 5 nodes, remove the edges, but edges are very important. The relationship between nodes are very important. That's why I model the data as a graph. So I cannot flatten the graph as number of nodes and neglecting the edges, because now I will lose a variable information, which are the edges connecting the nodes. Graph data have some interesting properties that make it difficult to work with using MLB or CNN. So I cannot say can't. I can use MLB and CNN with graph data, but I have to lose the connectivity, which are the variable information embedded in the graph nodes. So that's why I have to use what's called GNN, graph neural networks. So why graph data is different? Why graph data is different, and I cannot apply MLB and CNN directly on the graph data? First, size and shape. So if I have a graph, the size and shape of a graph might change within a data set. If I have a molecule, this molecule may have different number of atoms, so I will have different number of nodes for each graph. So the number of nodes in each graph in a data set is not fixed. Okay, so images also, I can have different images, and each image will have different size. This is the same problem. But in images, I can do resize, I can do bed, I can do crop to make all the images consistent. I cannot do this in graph, because if I have a graph with 5 nodes and I have a graph with 6 nodes, I cannot remove these 6 nodes. I have to keep all the nodes. So I will have in the same data set different graphs with different number of nodes. The number of nodes are not fixed. I cannot remove these nodes to make the number of nodes consistent. But in the images, I can do resize and keep all the images the same width and height. The second difference is what's called isomorphism. Two graphs may look different, but still be structure identical. So if I have this image and this graph on the left, if I flip the images, I will have totally different image. But if I rotate the graph, yeah, you can see the graph like rotated, but it is the same graph exactly. The nodes are connected to the same nodes in the left or right. So changing or flipping the images will give you another new image, but flipping the graph will give you the same graph, the same feature, the same connection. And this is what's called isomorphism. The third difference between the graph and the image data is what's called grid structure. So images have clear grid structure. So you have the pixel in the north and the up left, the pixel and up right, and so on. But in the graph, you cannot have a fixed location for each node in the graph. Graphs are dynamic structure that may lay differently in space, and distance metrics such as Euclidean distance is not clearly defined in the graph. So these are three differences between graph data and image data, and that's why we cannot apply MLB or CNN directly on the graph data. A GNN is an optimizable transformation on all attributes of the graph. So I will have a graph. This graph will have node embeddings, edge embeddings, graph entire embeddings, the connection between graph, and the GNN will try to learn a new embeddings from all this information at the same time. For GNN, the input of the GNN will be a graph, and the output of the GNN will be another output graph with all the feature learned. So these models, which is the GNN, accept a graph as input with information loaded into its node, edges, and the global context. And the graph will progressively transform these embeddings without changing the connectivity of the input graph. So the fundamental idea of a graph neural networks is what's called representation learning. Representation learning, this is what all the deep learning architecture try to do. You have input data, you have patient with EHR records, with MRI data, with C data, with genomic data. This is a raw data, and you want to learn what's called representation learning from this data, so you can apply classifier or regression on the representation of this data to do classification or to do regression on like on the patient data to see if this patient will have a disease or doesn't have the disease, etc. So using all the information about the graph, including the node features, the connection stored in the adjacent matrices, the GNN output a new representation, what we called embeddings, for each of the nodes in the entire graph. So this is the graph. I have a graph. Each node will have its own embeddings and the connection between nodes. I will input this entire graph to the GNN, and the GNN will output a new graph with the same structure, the same nodes, the same connection, but each each node feature will be changed, and this is what's called representation learning. I will go through animation, try to show you how these orange embeddings are learned from these blue embeddings from the left of the graph. So GNN input is a graph, GNN output is a graph. So what GNN will do? GNN will try to learn a representation for each node and the connection between these nodes. So these node embeddings, this is the orange ones, these node embeddings contain the structure as well as the feature information of other nodes in the graph. So each node knows something about the other nodes, the connection of these nodes, and its context in the graph. So now if I'm this this node, now I know something about myself. I know something about my neighbors and the connection between me and my neighbors. These embeddings can finally be used to perform prediction. After learning these embeddings, I can use these embeddings to do classification or do regression. The way how to use them depend on the machine problem you want to solve. If I'm doing node level prediction, I will take each node level prediction, pass these embeddings to classify or regression. If I'm doing edge level prediction, I will take the two nodes connected to each other embeddings, try to merge them somehow, and pass this to a classify or regression. If I want to do graph level prediction, I have to convert all these embeddings to just one embedding represent a graph and pass the resulting embedding to a graph classifier or a graph regression. So if I want to do node level prediction, I will use node embedding to predict the class label for unlabeled nodes. So if I have these embeddings, I will pass these embeddings to a classifier, and I will predict the label only for this node, using only these embeddings. If I want to use graph level prediction, I have to convert all these 5 embeddings to just one embedding and use it to classify or regress information about the entire graph. So using GNN, similar nodes with similar feature or in similar context will lead to similar nodes embeddings. And similar graph will lead to similar graph embeddings. That's why the classifier will be able to differentiate between nodes and differentiate between the entire graph. Also, I can learn the edge embedding, not just the node embeddings. I can also learn the edge embeddings for the edge connecting two nodes in my graph. So how do GNNs work? So inside the GNN, there are plenty of what's called message passing layer. So inside the GNN, inside a graph neural networks, there are many of what's called message passing layer. I will explain message passing layer in more details in the next couple of slides. So inside GNN, there are what's called message passing layer. The graph will pass through this layer one after the other, and after that you will have another graph output from the GNN, but with each node learn more information about itself and the other neighbors in the graph. So what is the message passing layers? These are the core building blocks of GNN, which are responsible for combining the nodes and the edge information into the node embeddings in the right. Let's see an example of how message passing layers taking a graph as input and output graph as output. So you can think of message passing layer as three-step. First, gather. Each node will collect its neighbor node's information. Then aggregate. Each node will combine the gathered information from its neighbor. And third is the update. Each node will update its embedding according to its embedding and the aggregated messages from its neighbor. So the message passing can be represented in three steps. Gather. Each node will gather information from its neighbors. Aggregate. The node will merge or combine the aggregated messages somehow. And then the update. Each node will update its information according to what it has and according to the update, the aggregated information gathered from its neighbor. So this is what happened at every GNN layer. So node exchange information and learn context from their surroundings. Message passing layer make the learned embeddings aware of the graph connectivity. Let's see in the next slide, we will visualize this message passing layer step by step, so you can actually see how information flow through the graph. Okay. Let's assume this is our input graph. You can see the yellow node number one, with the yellow node feature embedding. This is the embeddings for this node. This is the node that we will focus on the following. To update the state, of node number one, we will collect the information of the direct neighbors, which means we perform what's called message passing. So we will have the current node state. This is the current node state. And the direct neighbors states. We will denote this by H. So H1 is the yellow node information, and H4, 3, and 2 are the embeddings of the direct neighbors, which is 2, 3, and 4, to the focus node number 1. So this is the first step. This is the gather. So each node gather the information, the embeddings of the node of its neighboring nodes, the direct neighboring nodes. Then we will do the aggregate. These three messages, this 4, 5, etc., will be aggregated to have just one embedding representing information from our neighbors. And then I will merge what I have with what I aggregated. And this is the updated embeddings for the yellow node. This is the new embeddings now for the yellow nodes, and this will be happen for all the nodes in the graph at the same time. So number 4 will do the same, number 2 will do the same, number 3 will do the same, and number 5 will do the same. Gather, aggregate, and update. What you can see now, node number 1 doesn't have any green embeddings. What I mean, node number 1 doesn't have any information about node number 5. Why? Because node number 5 wasn't its direct neighbor in the first. But you can see node number 4 knows something about node number 5. Node number 2 and 3 doesn't know. So I will pass the same graphs, this new graph, to another layer. to another message passing layer, and I will do the same. So I will do gather the information of its direct neighbor. Now the embedding of 4, 2, and 3, the embedding of 4 knows something about 5. So after doing the aggregate and update, you can see that the new embedding of node number 1 now has something to know about the green node. So if you pass your graph to a message passing layer, you get information about your first hub. Your first hub means your direct neighbor. If you pass the output graph to another message passing, you will collect information from your neighbor's neighbors. If you pass the graph to a third message passing layer, you will collect information from your neighbors, and so on and so forth. So the more message passing you pass the graph on, the more information, the more neighbors you will collect information from. And this is good and bad at the same time. Do anyone know what is the bad effect of collecting information from nodes, from all the nodes in the graph? Should each node collect information from all the nodes in the graph?
Although it may increase accuracy, however, the risk of hallucinations may be increased if let's just say, increases the input from the diverse set of nodes. Is that correct?
Yeah, you mean the nodes embeddings will not be diverse. So this is what's called over smoothing. So if you pass the graph to many message passing layers, each node will collect information and will know information about all the other nodes in the graph. And in this case, the embedding of each node will not be different than the others. And in this case, you cannot use these embeddings for classification or regression. So you will have all the nodes will have more or less the same embeddings. So we have to use carefully the number of message passing layer I want to use in my model. If I want each node to learn like about neighbors or neighbor of neighbors in like 3 steps, so I have to use only 3 message passing layer. And this is like a parameter you have to validate. If you have a validation data set, you can try different number of message passing layers and see the accuracy and try to cross validate this hyperparameter. So after this message passing layer, I can do like many of them. I will have for each node the new learned embeddings, and these embeddings for each node can be used directly for node prediction, or I can combine all these nodes at just one embedding, and I can use just one embedding for whole or the entire graph prediction. So I started with each node embeddings. I end with embeddings for each node, but with information from its neighbors. This is the information I will use for prediction or classification for node level prediction, and I can combine them, and I will use the combined aggregated embedding from all these 5 embeddings to represent the whole graph, and I will use this embedding for the entire graph prediction or regression. So this is the basic idea of GNNs. Iteratively learn new embeddings by combining the node information of the local neighborhood. Iteratively, I mean we first learn something about the direct neighbors, then about the neighbors of neighbors, and so on and so forth. Let's talk about what's called computational graph representation. So if I have this graph, I want to visualize how deep we dive in the graph from each node perspective. So for example, if I want to do graph representation or computational graph representation for the Euro node, in the first step, Euro node will aggregate information from its 3 direct blue neighbors. It will do update and aggregate and update. In the second message passing node, the Euro node will collect the neighbors of neighbors. So the Euro node will collect information from the green and the other yellow, blue nodes, and do aggregate updates, so on and so forth. This graph is called competition graph, and it will visualize in each message passing layer what are the neighbors and what each node will connect from its neighbors and its neighbor of neighbors, and so on and so forth. So the number of layers in a GNN define how many neighbors hop we perform. And as I just tell you, and Dr. Mara just mentioned, this is a hyperparameter. I have to be careful when choosing the number of message passing layers, because the number of hops which will relate to the number of message passing layer, the more message passing layer you will add to your GNN, the more neighbors information you will collect. So if you increase the number, you will collect information from many neighbors. And if your graph is small enough, so each node will have more or less the same embeddings. So the nodes will not be different from each other, and we call this over smoothing. So it's very important to highlight the number of hops or the number of message passing layer, and this is very important hyperparameter. You have to validate, or you have to cross validate using your validation data to choose the best one that relate to your problem you want to solve. So the number of layers depend on the learning task. Local area of the graph might be relevant for the prediction. So if I have a social network graph means each node will represent persons. So if I want to know about you, I think that 3 or 4 or 5 hops will be sufficient to collect information about you and your friend or friend of friends and friend of friend of friends. So stacking too many message passing layers in a GNN can also lead to what's called over smoothing. And if you add more message passing layer and you get this over smoothing problem, the node embeddings become indistinguishable from each other, and this will lead to wrong predictions. So how to do the message passing and the aggregate in a mathematical way. So now HU of k is the embedding of the node number 1. Now I will do this for node number 1. So HU of k is the node embedding of the embedding of the node, the yellow node number 1 at layer k, and HV of k are the embeddings of its direct neighbors. So aggregate means I have to combine the 3 blue embeddings to just one embedding. Update means I have to combine the yellow embeddings with the aggregated 3 blue embeddings, and the update means change the embedding of node number 1 to be the updated version after doing the combination. So what update and aggregate I can do? So for the aggregate, I can do mean, I can do max, I can do normalization sum, I can do neural networks to learn the aggregation. For the update, I can do also mean, max, concatenation, etc. But your choose between update and aggregate should be differentiable functions. So you can learn these parameters for these functions. So whatever you choose, you have your function for aggregate and update should be differentiable function. Each combination between update and aggregate give you a kind of GNN. So if I use mean and mean for update and aggregate, this is a GNN. If I use max and mean, this is another GNN. If I use max and normalized sum, this is a different kind of GNN. All the GNNs we will call GNN variants. So GNN variants is the same GNN, but you have to determine which function are you going to use to do the aggregation, and what function are you going to use to do the update. I have a question here. Why the mean is the best one to do with aggregation? Why using mean? How many neighbors each node will have? It's a fixed number or is it like a variable number? No answer. Why I have to use mean to do the aggregation? Because each node will have a variable number of neighbors. So the mean will give you just one embedding. If you pass 5 embedding to the mean, then the output will be just one embedding. If you pass 100 embeddings to the mean, the output of the mean will be only just one output. That's why the mean, max are the preferable function to use as aggregation. So this is called what GNN variance. We in the state of the art we have GCN. GCN is graph convolution networks, and the GCN will use the self loop as update and will use some of normalized neighbors embeddings as aggregate. We have the most famous one is GraphSAGE. It's a GNN, but it uses addition or concatenation for the update, and it will use mean neighbors embeddings for the aggregate. We will have GATs, graph attention networks, in the GNN variant. It will use self-loop for the update and the attention coefficient for the aggregate. So the graph variance is the same message passing layers, but it will use different function for aggregate and different function for the update. There are plenty of GNN variants in the research domain. If you want to have a look for one of them, but as I mentioned, the only difference is what function you are using to do the aggregation and what are the function you are going to use to do the update. Now let's start the third section, which is hands-on with PyTorch Geometric. In this section, we will use PyTorch Geometric, which is a library built on PyTorch to easily write and train graph neural networks. Maybe plenty of you don't know anything about PyTorch. PyTorch is a very famous deep learning library built on Python that you can use to build your deep learning architecture like MLB or CNNs or transformers, and they help you how to train, test, and validate these models. PyTorch Geometric is another library built on PyTorch, and PyTorch Geometric is just specialized with GNN. So if you want to use GNN with PyTorch, you have to install PyTorch Geometric. It will help you to generate graph, to learn graph, to build GNNs, and to train and test your model. The first tutorial I will talk about, I will do node classification with graph neural networks. I will share the notebook now with you, and I will go step by step with it. Now you can see the okay. Now you can see the notebook.
Yes, doctor, it's visible.
Okay. I will not go deeply in the code. I will just show you what's node classification and what the result if I use graph neural networks or if I use multi-layer perceptron, and how the connections and the representation of graph will make the learning processing better and the accuracy more better than using MLP. In this node classification example, I will use Cora dataset. This is a citation network. So each node is a publication. is a publication document, and the connection is the citation between them. So if I have a publication and I cite these three papers, so these three papers I will connect to them. So I will have three edges connecting my node with these three nodes. So this is a publication citation network. Each node, each node will have a 1,433 dimension back and forth feature embeddings. So I will add to each node a text embedding that represent this publication. Two nodes or two documents, two publications are connected if there exists a citation link between them. So if I have I published a paper and I cite a visual in graph encoder paper, so there will be a connection between my paper and the paper I cited. So this is the graph. So each node will represent a document or publication. Each node will have 1,433 feature vectors. This is the information I will store for each node in the graph. Two nodes in this graph will be connected if one of them cite the other one in the research community. So this code I will run this code to download the dataset. After the session, I will share with you the code and how to download PyTorch Geometric, and run the code in your machine in an easier way. Take some time to download the dataset from the internet. Okay, now I have the dataset downloaded. So I have only one graph. So the number of graph is 1. The number of features is 1,433. The number of classes is 7. So each node will be classified out of 7 classes. So this is the data I have. If you remember, I want to store the feature of for each node in the matrix called X. So X is 2,708. This is the number of rows, and 1,433 number of columns. So I will have 2,708 nodes in this graph, and each node will have 1,433 feature. Okay, so imagine this X as a square matrix. Each row will have 1,433 feature. This row will represent the feature of a node. I have 2,708 row of these values. So I have only one graph, and the graph has this number of nodes, and each node, each one of them will have this number of features. And then this is the edge index. Edge index will tell you which node is connected to whom. So it will be 2 rows and 10,565 edge. So this is the number of edges I have in my graph. The Y, you can see Y is the same number of nodes. So for each node, I will have the class of that node. Y is class out of 7. So I will have 0, 1, 2, 3, 4, 5, 6. So each number will represent a specific class for each node. I will take this information and I will pass them to MLB. MLB is the normal, traditional machine learning architecture. MLB will take the embeddings of the nodes, try to learn something from them, but without including any edge information. So it will learn from each node separately. They will not collect information from the neighbors of the nodes. So MLB will take the graph as input, but without doing any aggregation or update as we will do in the GNN. So I will neglect the connections. I will just use the node features and try to learn from them. Let's see how the MLB will learn and what is the accuracy after learning using MLB. So the accuracy is 59%. So using MLB, I could pass the graph to MLB, but in that case, I will neglect the edges. So I will tell MLB, this is the nodes, this is the feature. That's enough. There is no any connection. I will not say to MLB which node are connected to whom, because I cannot pass this information to MLB. MLB doesn't trade with the connection between nodes. Now I will create a GNN, a graph neural networks, and I will pass the same graph to the GNN. GNN is different than MLB. GNN will do message passing layers, will do aggregate and update. So each node will collect information from its neighbors and the neighbors of neighbors and so on. According to the number of message passing layer you will add to GNN. I will train the GNN. I think I have to run this first. I will train the GNN. So I will show now the data before before training the GNN, the data of all the graph nodes. As you can see, the yellow nodes, the red nodes, the green nodes are not distinguishable. So we have the embeddings of each nodes are different. After learning and passing the graph to the GNN, I will show you what the GNN learned now. The accuracy becomes 81%. And this is the feature the GNN learned. So the GNN learned and make the feature for the brown nodes at the same cluster. They also make the node of the green nodes, the embedding of the green nodes in the same cluster, the embedding of the yellow node in the same cluster, and so it could learn something from the embeddings and differentiate the different classes from each other. In that case, if I do classification or regression, I will get better accuracy, as you can see, is like 81%. I can get like 90 something, but just a small example. I just pass the graph to just two message passing layer. If I increase the message passing layer, if I increase the model nonlinearity, I will get better separation for the embeddings and also better accuracy. So this is just example how to use MLB and how to use GNN on the graph data. As I just mentioned, if you are going to use MLB, which is multi-layer perceptron, with GNN, the MLB will not look at the edges at more. It will only look at the node features. But using GNN, the GNN will look at the node features, the edges, the connections, and it will learn more information from the neighbors and neighbor of neighbors, and that's why the accuracy is better using GNN than using MLB. I will stop sharing. I think there's another example I can go through, but for the sake of time. I will share the presentation again. So let's move to the final section in the presentation, which is vision and graph. Vision means images. So I want to use images inside the graph. So the graph data could be like a electronic health record, could be MRI data, CT, ultrasound, whatever. As I mentioned, could be genomic data. So now let's talk about vision, about images. So if you have images like these, you can cut the images into pieces, and this is the grid structure. And also you can treat these batches as a sequence, and this is the sequence structure. And also you can connect the batches, you can treat batches as node and try to connect them somehow to create a graph. Actually, in the deep learning community, if you have grid structure, the best thing to use is the CNNs. If you have a sequence structure, the first architecture to use is the transformer. And if you have a graph structure, the best thing to use is graph neural networks. So if you have images and you want to use graph neural networks to learn something from images, the first thing you have to split the images. You have to divide the images into batches, and each batch will form node. And then you have to construct the graph. You have to connect these nodes, each node with its nearest neighbor nodes. And then after constructing the graph, you can pass the graph to a GNN and try to learn node embeddings or a graph entire embeddings. So in this example, I have this image, sorry. I will divide it into batches. Each batch will generate a nodes. Each node will be connected to its nearest neighbor. And then after constructing the graph, I will pass the graph to a network, which is a GNN with message passing layer inside. And after that, I will pass the learned embeddings to a classifier or regression to do any machine learning on the input images. Also, I can use vision in graph to do segmentation. As if you are familiar with machine learning, this is what's called the UNet, and this is the famous architecture we use to do segmentation. So if I have an image, I can divide it into batches, create graph, and pass the graph to this unit to do what's called image segmentation. So graph can be used with normal data and also can be used with images data to do any machine learning task you want to do. For medical images, I'm used to use graph neural networks to do Alzheimer diagnosis using brain structure MRI or brain function MRI. As you can see here in the images, I have this brain MRI, AT1 brain structure MRI. I can segment the image into 32 different region structure, and then I will extract information from each one of the 32 region. Each region will represent node. Each node will be connected to its nearest neighbor. At the time I have a graph, I have nodes and edges. I will pass the graph to GNN to learn embeddings for nodes, for edges, and for the entire graph. And then I will pass the learned embeddings to classifier or regression to do whatever I want, like Alzheimer diagnose or multiple sclerosis segmentation, and so on. So If you have a 3D MRI image and you want to use graph neural networks to do some machine learning using these MRI images, the first thing you have to segment MRI image into different structure regions, and then extract radiomic feature for each region, and then construct the graph. In this case, each region will represent a node, and the feature extracted for each region will represent the node features. Then you have to connect nodes, means connect regions. Each node will be connected to its nearest neighbor region. After that, you have a graph. You pass the graph to GNN layers to learn embeddings for each node, and then you can use node embeddings to do whatever you want on the node level, or you can combine all the node embeddings to have just one embeddings for the graph and to do graph level tasks. Last year, I participated in 3 different publications published in MICAI, Medical Image Computing and Computer Vision Conference. It's the biggest medical imaging conference in the world. Inshallah, next October in Abu Dhabi, Mohammed bin Zayed University will organize this conference for the first time in the Middle East. So you are welcome to join us in Abu Dhabi and attend the MICAI conference if you are interested in the medical imaging. In the last MICAI, which was in South Korea, we published 3 papers. All of them are dependent on graph neural networks. The first one was diffuse MS, in which we use structural MRI deformation field to do multiple sclerosis lesion detection. And also we published what's called ClinGrad, which is clinically guided genomics and radiomics interpretable GNN for dementia diagnosis. And also we published Magnet ED, which is a multitask spatial temporal GNN for interpretable prediction for back and conventional time in preclinical Alzheimer. I was so fast. I'm sorry, because some of the concepts and the mathematical stuff has to be explained to you if you are not coming from a computer science background or a mathematical background. And I know that most of you are coming from medical or biomedical background. I just want to give you a small insight about what's the graph, what's node, what's edges, what's the connection, why graph is better, why GNN is better than MLB for for your data, if your data can be represented as edges and as node and connection between them. That's it. And now we will open for question and answers if you have questions.
Thank you
First
again.
of all, congratulations, Doctor, on your publications, and would love to read more about it. This has been an absolutely insightful session on MLP, GNN, and computer vision. I will proceed by asking questions because I see there are a few in the chat. So the questions are from different parts of the presentation. Moving to the first one, it's in your field of work, can you share a concrete example where graph or machine learning model is used to identify patterns, support decision making, or predict outcomes? How does this approach add value compared to traditional methods?
Yeah, but compared to the traditional method, to using GNN with your data, which better to use MLB or GNN? If your data can be represented as a graph, if your data have connections, if your data have relationships, the best way to use to represent your data as a graph and use graph GNN. The example I just show in the code, I have some publications and some citation between the publication. The citation is the connection. The citation between the publication is the connection, is the relationship. If I pass the data to MLB, MLB will learn from each publication separately. You cannot add to MLB and to tell MLB which publication is connected to the other one. But if you want to benefit from the citation, and it's very, very important, if I am citing papers, for sure these papers will be the same class like me. If I'm working with AI and medical and healthcare, the publication I will cite in my publication for sure will be related to healthcare and to AI. So if you pass information to MLB, you will pass each publication separately. But if you pass your information as a graph to GNN, you will encode somehow the connections between the publication, so the model will learn not just the embedding of each node, but will learn from the information from the other nodes and other neighbors. So if you have
Uh,
data and if you can encode relationship between your data and you can structure your data and a graph, GNN will be better than MLB, for example. But if you have your data and there is no connection between them, just each data is separate than the other one, so MLB will be better than GNN.
okay. And just to follow up on that, like what would be an example where MLP would be better than GNN? Like in which scenario for if you have an example for that?
Okay, if you have EHR records, like for each patient, you have the blood samples, the electronic health record for each patient. So there is no any relation between this patient and that patient. So if I
Yeah.
have EHR record for patient, I will use MLB. Like if you have data about students, about professors and the interaction between students. Like these students will do a project with other one, and this professor are the supervisors for these students. So you will have data that are connected somehow. So representing this data in a graph using GNN will be better.
Al- Also, another question I would like to further elaborate, and this can be in a form of discussion. One of the things I noticed specifically, or ideas that I got while you were speaking, is now you speak about the electronic health record quite a lot. And we do understand now, I'm going to tie it to genetic testing. So we do understand some predispositions, genetic markers can be inherited and can alert us to when a patient might need a certain enzyme assay or pharmacogenomic test before administering a certain medication. Data, for instance, tying it back to adverse drug reactions experienced by their family members, parents, whether
Mm,
siblings, so on, can also alert us on potential medication that is specifically hazardous towards a patient. Do you agree in this manner, utilizing this data?
for sure. The work of Pharmedic, the data you are using is best suitable using graph neural networks.
Mm-hmm.
And I'm sure that if you, I'm not sure about what models you are using in your application, but your data is perfectly suitable to be used to be represented as a graph, because you have these relationships, you have this connection between patients and medications, and also maybe one patient can take two or more medication at the same time. So your data is can be represented as a graph, and your model can be GNN, and I'm sure the accuracy of your model will be better if you go this way.
Mm-hmm. Completely agree. I went through your research papers before the existing workshop, and I was very impressed with the work on Alzheimer's, as you mentioned, as well as multiple sclerosis. Now we know within clinical practice, Hafsa may be able to also elaborate on this manner. But when we examine different modalities, imaging and whatnot, there are certain markers or landmarks that we are able to exhibit by the naked eye. For instance, when we differentiate between malignancies or an abscess within an MRI, we can look at, for example, the ring enhancement lesions, the hyperintensity or hypointensity. What is the accuracy of the models to be able to detect the following progressive diseases early on, whether that be like an ischemic stroke or a arterial blockage or whatnot? Are the models capable of doing such, or do we need further, how can we say this, research work in this field before translational adoption?
Actually, this is what AI is doing now. AI can see what you can see with your eye and more behind. So there are a lot of markers that you can see by your eye, and many of them you cannot see by your eye. So, and also the correlation between the different modalities. Um, for sure, if you
Mm-hmm.
have PET modality, you have fMRI, you have structural MRI. By your eye, you cannot look at all these modalities at the same time. But with AI,
Mm-hmm.
AI can get information from all these modalities, try to learn a representation, and that's why it's very smart in disease diagnosis and classification.
Another thing I wanted to also emphasize on, I saved all my questions for the end actually. We spoke about embedding, and I wanted to discuss briefly on the field of omics. Now, we do understand when we conduct, whether that be single cell sequencing or whole exome sequencing, there are numerous factors that may attenuate a patient's response. I'm going to delve a little more into drug discovery, or let's just say treatment outcomes and predictions of such. Now, when we conduct these embeddings and be able to quantify, let's just say, protein expression like transcriptomics, as well as looking into metabolomics, as well as bringing methylation and epigenetics into the field. How advanced are current algorithms to be able to support and predict patient outcomes to certain treatment plans? And what is the current gaps within the research work? We have a lot of medical students within the workshop today, and you may plant seeds or gaps or inform us of problems that we may solve in our future careers.
Actually, to be honest, we start playing in this area. We have just submitted a proposal for a grant with DOH here in Abu Dhabi. Try to like do more research in this area using on the neurodegenerative diseases. So
Mm-hmm.
I'm just start searching and to see the gaps we want to fill. But I think in UAE there's no publication, a lot of publication related to this area. That's why we want to explore it more with Department of Health in Abu Dhabi.
Mm-hmm.
Um, I can share with you like the latest publication related to this like adverse prediction and the cost of ineffective treatment. But I'm focusing on multiple sclerosis, to be honest. Um, that's why we
Mm-hmm.
apply for this grant. But
Mm-hmm.
in my mind now I don't have like all the picture about the state of the
Mm-hmm.
art related to this one. But if you're interested, I can share with you some of the latest publication.
Mm-hmm. What initial, let's just, now it's out of curiosity, my question is, when we spoke about demyelinating diseases, what are the current areas do you believe are worth of investigation? What can AI introduce to this field that we as physicians cannot provide, specifically when talking about neurodegenerative or demyelinating diseases?
Yeah, in my opinion, we want to be specific in choosing the disease modifying medication.
Mm-hmm.
Disease modifying treatment, like I think the physician now is trying to do try and error, like give this
Yeah, correct.
medication and see what is the effect of it. And this is uh, uh, ineffective in terms of cost, and
Mm-hmm.
also may do more relapse for a patient with MS, for example. He's trying different medication and try to see the effect without knowing about the genetic aspect of this patient.
Mm-hmm.
So what we are trying to do now in our research, and maybe we can collaborate with Pharmedic in this one, is uh, to use a precision medicine. So we want to prescribe
Mm-hmm.
a disease for multiple sclerosis, for example, based on uh, the genetic information of that person. Uh, it may work with this person, but may not work with another person based
Mm-hmm.
on its genetic variant. So uh, this will save a lot of money. Will try to help the patient to be recovery as soon as possible, because try and error in these diseases and with kind of therapy is not like it's not, how to say, like not the best thing we
Mm-hmm.
have to do with patient, especially in UAE.
Mm-hmm. There's always room for improvement, and we applaud your work, Professor Mostafa. And hopefully, with the advancements within precision medicine and as well as preventative rather than reactive healthcare, we'll be able to change the way healthcare is delivered within the UAE and abroad, inshallah.
Inshallah. Inshallah. Rabbil Alamin.
Doctor, we have a question in the chat. How does GNN-based computer vision models compare as opposed to using transformer CNN backbone models?
Okay, this is the same question. Like all are very powerful, but according to the data and the structure of data, one is better than other. So using transformer try to learn general embeddings from the data. So you have to have a very huge data set to use transformer to learn from. CNN is specialized for images because it is used inductive bias as input is an image. So CNN is very perfect dealing with images. GNNs, as I just mentioned, is a powerful machine learning model architecture. If you want to use GNN and get better results, you have to encode your data, or your data can be encoded as node edges, as features, entities, and the relationship between them. If you have data, but these data are not connected somehow, there is no any relation between them, so GNN is not your choice. You have to move to MLB or transformer according to how much data you have. Transformers need more data. MLB or CNN needs like medium or small data to learn.
Before we move on to the next question, I would like everyone to scan the QR code and sign up for Pharmedic's newsletters. Additionally, I have also shared a link to fill the feedback form and the attendance form. So for the certificates. There was a question from previously within the chat. It was regarding the node level versus graph level. It can sound similar in practice. What is the simplest rule to distinguish them? And could you give one example where people often mistake a node level problem for a graph level?
Okay. Node level means you have a node embedding and you use these embeddings to do a machine learning task. Graph embeddings, you have just one embedding to represent the whole graph and use this to do graph level prediction. Let's give you an example. Okay, for the brain MRI image I just show, I can divide the brain MRI into 32 regions, and each region will represent a node, and each region will have its own embedding. So if I want to do a region specific task, I will use the embedding for each node to do the machine learning task. But if I want to do to give a class or a label for the entire MRI, so I have to combine the feature from all the 32 region to be just one embedding representing the whole image, let's say the whole graph, and then using this embedding to do a classification. So node embeddings, you will have label for each node in the graph. Graph embeddings, you will get a label for the entire graph all at once.
Thank you, Doctor. I believe that's it for the questions. Kindly share your questions if anything is unclear.
Feel free to communicate with Professor Mustafa at any time. He has attached his email addresses, and we will be able to connect you if ever needed. Inshallah, Professor Mustafa will be seeing more of you. If you have any more information on the, let's just say, forum that Hamad bin Zayed University of Artificial Intelligence will be hosting, and you would like us to circulate it within our network, we are happy to do so. If you have any other opportunities for the students as well as researchers with us, or if you would like to contact them directly, we are always here to help and support that, inshallah. Thank you again, Professor Mustafa, for your time.
Thank you, Dr. Mara. Thank you for the invitation and hosting me. Thank you, Rahim.